Hello! Welcome back to New Scientist Weekly, your curated selection of the week's science stories. I'm Claire Wilson.
And I'm Rowan Hooper. Welcome to the show. It's episode 190 and we're recording this on May the 10th. Coming up this week, we've got an incredible entry to the Eurovision Song Contest, which I can't wait to play. And in an unrelated music story, we're going to hear a church organ on Mars.
Marvellous! We'll also be discussing the evidence around vitamin D supplements and what they can do for you. We have a life form of the week that shares food with others, and Rowan will be discussing a new paper on climate tipping points in the Arctic. But first, lab-grown meat. Now it's been billed as a cruelty-free alternative to regular meat that has the extra bonus of being better for the environment. But is it too good to be true? Rowan spoke to our Australia reporter Alice Klein about a study that suggests it could be 4 to 25 times worse for the climate than regular meat.
Hi Alice, let's start off. Remind us, what is lab-grown meat and how do you make it?
Yeah, well, I should start off by saying that the companies that make lab-grown meat now prefer the term cultivated meat, as I guess that makes it sound less artificial or something. But it is made in a lab. So basically they collect some stem cells from a cow or a chicken or whatever you like, really. I mean, there's actually an Australian startup now that's making all sorts of exotic cultivated meats like quail and alpaca and anything you like.
Chimp?
Maybe chimp. Well, they actually made a mammoth meatball recently, but I was a bit skeptical about that. But yeah, so they get the cells, they put them in a growth medium, which is like a broth that contains lots of nutrients and growth factors that help the cells grow into a meat-like product. And you can keep growing more and more of the cells for years. So it does largely cut out the need for animals to make meat.
Yeah, and that's the idea that it's much better for the environment because you don't need land, really, because you're not farming animals and you don't have to grow food for the animals. And then you don't have all animals like cows going out there and belching methane.
Yeah, so it does sound like that on paper, but you do still need to feed the animal cells to make them grow. And that's actually where you run into some problems. So at the moment, all the things that you need to feed the animal cells, which are things like sugars, amino acids, salts, vitamins, and growth factors, they're all very energy intensive to make. So they have a large combined carbon footprint.
Why is that? Because it doesn't sound like they should have such a large footprint.
Yeah, well, for example, to obtain sugars, you need to grow crops like maize. And then to produce the growth factors, you need to have these labs where they actually extract them from cells. But then the really big energy suck is purifying them because they have to be really ultra pure to be used in the growth medium that the animal cells are cultured in. And this requires these really energy intensive methods like ultrafiltration and chromatography to make them pharmaceutical grade purity.
Okay, so that's why lab-grown or cultivated meat has such a large carbon footprint.
Yeah, so a recent study by some researchers at the University of California, Davis, they looked at the energy costs associated with producing and purifying all these individual ingredients. And when they factored those into the production of lab-grown meat, they found that its global warming potential would be 4 to 25 times higher than that of beef, depending on what... Yeah. That depends on what study you look at regarding the global warming potential of beef. But yeah, it does sound quite high.
That's shocking because, beef is horrendously bad, with all the clearance of land you have to do for it and then clearance for growing crops for feeding cows. So to be multiple times worse than beef is...
I know, it's surprising.
Yeah, it's shocking. But why does it all have to be so pure? Can't you just chuck in this stuff, the ingredients, into the cells and let them grow?
Yeah, that's sort of what I was wondering because I was thinking, like meat itself, regular meat isn't that sterile. So why do you have to have such pure stuff when you're making this cultivated meat? But it's actually about if you have any traces of contaminants in your growth medium that you're growing the animal cells in, so contaminants like bacteria or bacterial toxins and things, then the animal cells won't grow because the bacteria will multiply much faster. So then you can't actually make your cultivated meat.
Yeah, well, maybe you should just make bacterial food and eat that, actually, microbial food. But apart from doing that, what's the way around it?
Well, at the moment, all cultivated meat is grown in this very pure pharmaceutical grade growth medium. But the cultivated meat companies say that they're working towards using less pure food grade growth medium, which is partly to reduce
Right.
the carbon footprint, but also because the pharmaceutical grade stuff's really expensive. And that might explain why no one has actually been able to really scale up cultivated meat production just yet.
Well, because I was going to ask you about scaling up. So that and that's why they're so expensive at the moment as well, right?
Yeah,
So expensive to get a burger. And
exactly.
okay,
Yeah.
so that's why we're using pharmaceutical grade materials to
Yeah.
make them. Yeah.
Yeah. And so, the companies say that they're hoping to move to food grade supply chain eventually, but some experts are dubious about whether this will be possible because they say even trace amounts of contamination can destroy animal cell cultures. And it can be kind of confusing because there are a few other studies floating around that say that lab grown meat will have a lower climate impact than regular meat. But
Mm.
those studies assume that food grade ingredients could be used instead of farmer grade in the future. And that's something that's still very uncertain.
I mean, what about if you sort of tried to make it as renewable as possible in the production steps? Could that sort of significantly cut down the carbon footprint?
Yeah, if you used renewable energy, to power your supply chains and the cultivated meat facilities, that could, maybe lower the carbon footprint a little bit. And there has been some talk about using the land that's been freed up by less animal farming to build solar farms and things like that. But I mean, if you think about if the carbon footprint is going to be 25 times higher than regular meat, then that is a lot of a lot of extra solar farms and things that you're going to need.
Yeah, it sounds like it's going to be an absolute luxury with a gigantic carbon footprint.
Yeah.
I mean, is it too good to be true then, do you think? Lab grown meat.
Well, its major advantage is still obviously that it's a lot kinder to animals. Um, Personally, I have to admit,
Kinda, it doesn't kill animals. Yeah,
yeah,
yeah.
yeah. I personally wonder if people will actually want to eat it. But assuming that they do, I think it's really important that we address its climate impacts because there's already been about $2 billion that's been invested in this sector. And we still don't actually know if it's going to be better for the environment.
I mean, it looks like plant-based mimicry of meat is going to be the way to go because that's getting so good, isn't it? I mean, I eat that all the time,
Me
and
too.
it is getting really good. And maybe at least in the near term, that's going to be the way to go.
Yes, I definitely agree.
Now, we talk about climate tipping points a lot on the podcast for good reason, and that's because they're processes like Amazon deforestation and Arctic ice melt that if they go past a certain threshold, the loss becomes irreversible and self-perpetuating, and that could speed up climate change and have unforeseen consequences on the planet. I mean, they're really quite scary things that we should avoid if we possibly can. Now, this week there's a paper out in the journal Nature Geosciences that presents evidence that we may be approaching a tipping point in the Arctic, and this concerns an ocean circulation system called the Beaufort Gyre. So to explain this, we're joined by two of the authors of this work, earth scientists Harry Harton and Michelle Samados from University College London. Michelle, you've likened the melting of the sea ice, the melting of the blanket of sea ice over the Arctic, as like pulling a blanket off a sleeping monster.
It's really an analogy as a person waking up. So I've asked in the past, are we waking up the sleeping Arctic Ocean? By removing this blanket, suddenly the winds are stirring up things and things are kicking out. One thing that's happening is spinning up and down of the Beaufort Gyre. So the winds are suddenly able, or at least we understand, they're more able to have an action, a direct action, or via the ice into the ocean underneath. And what we've observed in the last 10 years is that there is an accumulation of 10,000 cubic kilometers of fresh water. That's about 10 billion Olympic swimming pools of fresh water accumulating in this region. So we talk about that in this paper, and we're trying to understand the fate of this water.
So what can this accumulation of fresh water do to the circulation in the ocean?
So this is a huge amount of fresh water. I think it's equivalent to about 30 years of Greenland melting fresh water into the oceans. And so where it ends up is quite important for general circulation. What could happen is that normally deep, cold, dense waters in the Arctic are diving deep in the ocean due to gravity. If we put all this fresh, buoyant, light water into the regions where normally this happens, we could prevent that to some degree from happening and slow down the whole circulation or ventilation of the ocean. And this could have implications for climate even at mid-latitudes, in England and so on.
Does this mean it can have a knock-on effect on the Atlantic meridional overturning circulation, the AMOC, the Atlantic conveyor, which brings warm water from the tropics up to the North Atlantic?
Yes, if you bring this 10,000 cubic kilometers of fresh water into the wrong region in the decades or years to come, you could slow down at least this AMOC, as you said, Atlantic meridional overturning circulation, which is one branch of the Great Conveyor Belt or thermohaline circulation. And this has implications for, again, climate in the mid-latitudes. Normally, this branch brings warmer waters to higher latitudes and essentially warms up places like the UK.
Harry, can you talk about some of the impacts we could see if this conveyor of warm water is disrupted?
Yeah, so the idea of the meridional circulation is it brings warm water to the North Atlantic. So if you compare the UK to many other places in the world that are similar latitude, they have much colder winters than we have. Like ours hovering around 0. If you cross the Atlantic to the other side, to Newfoundland, hovering around -10. It's a huge difference. And that is mainly due to the warm ocean. The warm ocean comes up, brings low latitude water to the UK, and the warm ocean means you get warmer atmospheres because the atmosphere gets heated by the ocean, and that brings warmer weather. If you turn off the overturning circulation or adjust it, that warm water maybe will only come up as high as Spain. And that leaves us with a whole lump of cold water sitting next to the UK, which in the winter, where we would need the atmosphere to be heated by the ocean to keep our temperature warm, that's a big 5-10 degree difference. So that is the case example of this. And there is evidence in the past, as we go back to the end of the last ice age, the collapse of the Laurentine ice shelf, like that has been seen to happen before. There's other examples where people say, I'm not sure if it's so conclusive, like the mini ice age, I think in the 1600s, there's similar low temperatures, and that is proposed to be also a similar aspect of this North Atlantic. But it's very difficult to predict. It's very difficult to understand. It's also very difficult to go back to paleo records and actually piece together what happened over the timescales we're looking at now, over what changes that caused, and is it even possible to change the AMOC? There's evidence recently, because there's lots more data going out, loads more ocean data in the last 5-10 years, showing the AMOC is changing, but because our data does not go back long enough, we don't know, is this just a normal oscillation? Is this just normal variability you see in it? Or is this a new change that we've done? So quite often with the ocean and these large systems, the normal oscillation, for example, say an El Nino sort of event oscillation, these variability which just happen every now and then normally are of the same time scale as how long we have data for. Very hard to tell which one's which. Look at, say, the Arctic, that's a special case example because it's very easy to tell what's going on. Atmosphere's warmer, there's less sea ice, and you can see that's a very clear change. Ocean beneath, very difficult to know. It's very difficult to know what's going on at all levels of the ocean due to the size and the depth of it. So that's why we have all these monitoring arrays, all this data to look at, to check for trends, check year upon year what is going on.
10 years ago, we discovered, colleagues of us, this big freshwater bulge in the Beaufort Gyre, 8,000 cubic kilometers. In the 2000s, the water piled up in the Beaufort Gyre. What this study finds is that it has stabilized in the last 10 years, let's say. And so this freshwater is now kind of stored in this region and it's not growing anymore. It couldn't, if we study the physics, it had to stop at some point. So now we have this freshwater stable, and at the same time we are monitoring exchanges of freshwater at lower latitudes in different straits in the North Atlantic. So we are trying to connect the dots between this freshwater there and the exchanges at lower latitudes. So if we detect this freshwater coming souther, then we might have to start to worry or to think about what's happening.
So, contrary to some reactions to your study I saw on Twitter, it's not saying we're approaching a tipping point so much, is it? But what is the study telling us?
This system is a great example of how climate change and the need to cut emissions, which is really important, and we should be doing everything we can as soon as possible, to say it's a global problem. And you may look at climate change and say extreme events, for example, Arctic sea ice loss, massive losses, huge change, Extreme events are only there. We don't need to worry about it if we don't live there. Extreme events in one part of the ocean, particularly the ocean, it can affect the whole ocean and global climate. These things are so interlinked. How are they interlinked? Over what time scale? Very hard to answer. So this may not be a tipping point. This may not be complete sensational doomsday scenario. I think a lot of scientists would be very surprised if it was. But it is great evidence to show that this is a global problem. You may see extreme events in the other part of the world and be tempted to say, it doesn't affect me here. Yes, it does.
Claire, now, have you ever heard a church organ being played on Mars?
I can't say that I have.
Yeah, no, well, so no one's expecting this, but that is what we're going to hear now on the podcast. But first, let's hear the same church organ being played on Earth.
Very familiar sounds, okay.
Yeah. So that was played by Timothy Leighton, who's a professor of ultrasonics at the University of Southampton here in the UK. And he developed software to alter the sound of the music.
This is a church organ that was played on Earth, and then I've transposed the sound for how it would sound on Mars, Venus, and Saturn's moon Titan. And then they've all played together. So we've had a simultaneous concert from the 4 organs, and that's what it sounds like.
Wow, well, that's really impressive, but why is he doing this?
Yeah, that's a good question, Claire. And one which I asked him. He wants to promote the use of acoustics in space, right? So we're talking about going to Europa. If you landed a probe on Europa, that's Jupiter's moon, Europa, it's got this really thick ice sheet, and underneath it is a liquid water ocean. And instead of having to drill through this really, really thick ice sheet, you could potentially listen through the ice and listen to the water underneath and learn quite a lot about what's going on there. So, this is the sort of thing he proposes.
Okay, that makes sense. So we've had sounds of Mars on the podcast before, haven't we?
Yeah, we have. And that's something else that Timothy Leighton talks about. We have had sounds on the podcast. So I went back to the NASA archive and I found this. That's the Perseverance rover driving across Mars. And then there's this. This is a dust devil, which is basically a gust of wind blowing over the rover.
Wow, it's quite something to think that that's the actual sound of the wind on another planet. That's not made up, is it? That's actual sounds recorded on Mars.
I mean, I know it sounds like I've just been amiss with my microphone, but no, that's actually the sound of Mars. Yeah, actually the sound from Mars. Here's some more sounds from Timothy Leighton. What you're going to hear first is the voice of a child on Earth, and then that voice transposed to what it would sound like on Mars.
Mars. Mars.
That's very cool.
Yeah.
But again, why is he doing that with speech?
Well, if you can predict the sounds of things like voices, which are very complex, if you can predict accurately what they would sound like on other planets, then you can use that software to predict the properties of other vibrating things, and that will help design them for when you actually go there on different missions. So all this, by the way, is from the American Society for Acoustics, which is going on this week.
Time for a break and some messages.
Yeah, we've got an online event coming up on Wednesday, the 17th of May, opening the infrared treasure chest with the James Webb Space Telescope.
Join Nobel Prize-winning astrophysicist John Mather as he discusses NASA's groundbreaking telescope.
For more information on this online event and to book your ticket, go to newscientist.com/space telescope.
It's Life Form of the Week time, and this week we've got chimps.
Yeah, this is an interesting study about food sharing, which of course is something that is very common in human societies, but we actually didn't know whether other apes do it too.
Okay, do they?
They do. Chimps and bonobos do exchange food with others, but only if they've been shared with first, which is what 4-year-olds do. So they have the same food trade capability as little kids, basically. So the researchers have done this on captive chimps, and they gave them the choice of pulling a plate with a treat on it towards their own cage, or pulling a mechanism that also delivered a treat to them and to the cage of another ape, another chimp. And most apes actually chose just to feed themselves alone. But if you rigged the test and make the chimp sort of deliver a snack accidentally to the neighboring chimp, then when they try it again and it's unrigged, the partner will deliberately share with that other chimp. And then the researchers did it with the same test with human kids.
Oh, and what if the children don't like the treats? I mean, then they might not mind sharing it anyway.
Yeah, actually, they controlled for it. So they chose treats that each participant really valued. Chimps got peanuts, bonobos got grapes, and children got sweets. And basically, when apes saw that another ape had shared with them, they returned the favor about 70% of the time, and about 80% of the children made the same choice. And when children felt snubbed, they were unlikely to share food in return. But some apes did still share their food around half the time, even if the partner was initially selfish.
So this is kind of shedding light on the evolution of altruism in human evolution, isn't it?
It is. And it basically suggests that human ancestors had to domesticate, really self-domesticate, downgrade their aggressive, dominating tendencies around food and foster cooperation and social connection. Now, Claire, you've been working on a story about the health benefits of vitamin D this week.
Yes, another one.
Well, yeah, it does feel familiar, but that's because there's been controversies over the claimed benefits for vitamin D, haven't there?
Yeah, that's right. Yep. So obviously, we've long known that getting enough of every vitamin is important for your health, but supplements of vitamin D in particular, which we normally get this vitamin from our diet, and it's also made by our skin when we're exposed to sunlight. This has been the subject of several claims that have turned out to be false, including that supplements can protect against cancer, heart disease, and COVID-19 too, actually.
So why have they turned out to be false?
Yeah, well, these health claims usually came from a particular kind of research called an observational study, and these are faster and cheaper to do than the most rigorous kind of medical evidence, which is the randomized trial. So just to recap, a randomized trial is when you take, say, 100 people, and on the toss of a coin, you randomize them into taking either a vitamin D supplement or a placebo tablet. And then at the end of the study, you see if the vitamin D group were protected against COVID, for example. Now, an observational study is when you simply observe people's vitamin D levels, say by taking blood samples, and you see whether higher levels correlate with less COVID. But there are problems with that approach. So for one, a big factor affecting your vitamin D levels is how much you go outside, and people who go outside more are likely to be healthier to start with. So that's why in the past these observational studies have wrongly suggested that high vitamin D causes better health.
So what's this new study? Is it a randomized trial then?
Well, no, it's a third kind of study, actually, quite a new kind. This uses natural random genetic variation in people's vitamin D levels to stand in for the randomization process of a trial. And this found that people with genetically higher vitamin D levels are less likely to get psoriasis, which is an autoimmune condition where the immune system attacks the skin. And this makes sense because a similar kind of genetic study has previously shown that vitamin D protects against multiple sclerosis, which is another autoimmune condition. So it does seem there is this connection between higher vitamin D and some kinds of autoimmune diseases.
Okay, but you just told me that the best kind of medical evidence is a randomized trial. We know that. But we still haven't got a randomized trial to show that vitamin D protects against these kinds of autoimmune diseases, right?
Yeah, fair enough. So I think this genetic kind of study, it's called Mendelian randomization, by the way, after the 19th century Austrian monk.
Gregor Mendel.
Yes, the
Yeah.
father of genetics. So it's still relatively new in medical research, and we don't really know where to place it in the hierarchy of different kinds of research. So we do still need a randomized trial to be done looking at this question after all.
So look, what's the take-home message at the moment? Do we need supplements of vitamin D or not?
Well, we don't know for sure, but this latest study is another piece of evidence suggesting they do reduce your risk of some autoimmune diseases. But I should also just say that in many countries, including the UK, the US, it is recommended you take vitamin D supplements anyway for strengthening your bones, although of course not everybody does.
Now, finally, we're going to play out with this Eurovision song. So it's the Eurovision Song Contest this week. This is a massive event where all the nations of Europe take part in a competition to find out who has the best song of the year. And to mark this important occasion, the SeaLife London Aquarium has had a frankly genius idea of putting hydrophones in its aquarium and making a song based on recordings of the underwater animals. And that is the banging track that you can hear now.
Yeah, based on some previous Eurovision songs, I think that could
win.
Actually be a genuine Eurovision entry.
They've called it EuroFISHion, the track.
Oh,
I wish they did enter it, actually.
No, that's ruined it for me, the name.
Well, look, it's great PR for the aquarium, but the kind of important point on the side of this is that we can learn about biodiversity using hydrophones, as we had about freshwater on the podcast recently as well, to listen to the organisms in the ocean, like coral reefs, fish, even seaweed and plants in the ocean and the deep ocean.
Thanks for listening to New Scientist Podcasts. Do subscribe to our show and check out our archive. It's all free. We'll see you next week.
Bye for now.
Bye.
This podcast is produced by OG Podcasts. Find out more at ogpodcasts.co.uk.